Hi, everyone. Sorry about that. My microphone was giving me issues, so I don't know if I got it corrected. So if I sound funny, can you let me know in the chat? And then we'll get started. If everything sounds okay, we'll get started. Just kind of wait here for a minute or two. So if the audio sounds bad, let me know. Sounded like I had a really deep voice when I was trying it out right before we started. Okay, good. Sometimes, so I always test it out before I we go on, and I record a copy, listen to it, and see how it sounds. And for some reason, every recording I made, I had this really deep voice. Um, so I was trying to get it, but I'm glad the streaming side of it works all right. Um, okay, so today we're gonna just apologies for the late start, but that's fine. So first, just a few announcements before we kind of get into the main part of the lecture here. So I posted a few things on our course website that hopefully you've read through or you have some time today to read through. So first of those is just a reminder about recitation exam 6, which we have in recitation when we get back from fall break. The next post I made in the news feed there is for scheduling the follow-up exam 6. So and then I made one other post this morning just kind of outlining everything that we have remaining in the course, just so that you can kind of go through and plan your schedule for our course and then all your other courses. So in terms of homework, we have 8 homework assignments that are going to be assigned. So we have 4 of them currently assigned, and we have 2 due tonight, and then we have 2 due on Tuesday night when we come back from fall break. Then in the last 2 weeks of class or so, we're going to be doing a few other topics. So we'll have some homework assignments for those. And those 4 homework assignments, they're not posted yet, but those will be due before our final exam. So those will be due, we'll have a few weeks for those. So that's for homework. For the exams, we have recitation exam 6, which is the week we come back. And those will contain the new material that we're doing. So there'll be 6 questions of new material. And then there'll be the follow-up questions from exam 5. So you'll have your second opportunity for any exam 5 questions that you didn't get correct the first time. So that's the week after fall break. Ideally, or what we're looking at for the last week is its follow-up exam 6. And this is going to contain all the questions from exams 1 through 6 that you can try again. So it'll be kind of like your third opportunity for all of those questions on exams 1 through 5, and it'll be your second opportunity for the exam 6 questions. So we have exam 6 in week 14. We're going to have this kind of follow-up exam for all the exams during the last week of class. And we're going to be scheduling that so everyone's taking it at the same time. So if you can, complete the Google form and the little survey there, just indicating when you're available, just so we can get that scheduled, hopefully later tonight. So that's the follow-up exam. And then we have the final exam as well. So we have our cumulative final exam. It's a department final, and that's during finals week. So we have really our recitation exam 6 with new material, follow-up exam 6, which is kind of questions from all the previous exams that you can retry. It's optional, so you don't have to take it if you don't want to. And then we have our final exam during finals week. Now, on that post on our course website, it's called Fall Break Announcements. I mentioned a few things. So there's going to be one more homework extravaganza that'll happen during week 15. But I'm just kind of giving you a heads up now so that you can kind of go through and any homework assignments that you don't have complete, you can work on those. And, work on them. You can still check your answers. And once all the homework sets are reopened for that last time, you can go through and submit everything. So there's going to be one more homework extravaganza. And then the other thing is for the final exam, any question on I call it the final exam extravaganza, but any question on the final exam that is testing one of our learning outcomes, if you still haven't gotten that one correct from the recitation exams, if you get 90% or above for that question on the final exam, then that would count for mastery. So I would go back and find your recitation exam score for that question, and if you still had progressing, I would change it to mastery. So essentially, think of the final exam as one last chance. It's your fourth and it's basically your fourth chance for some of these questions. So if you don't get them after follow-up exam 6, well, there's still the final exam, so still keep working. And if you score 90% or higher on an applicable question, well, then that would go towards your mastery check for that learning outcome. So there's kind of 3 exams. One of them is optional. And the rest, the follow-up exam 6 is optional. There is a question, the final exam, how will it be structured? So it's a department final, so everyone taking Math 141 is going to be taking the same final exam. So it's not going to be structured exactly the same way as our recitation exams. But I mean, basically, the recitation exams are really preparing you for the final exam. So, there's going to be questions on derivatives. There's going to be questions on integrals. So questions on limits. So basically, things might be organized a little bit differently, but ultimately our recitation exams are going to prepare you for that final exam. So the questions will have a very similar kind of feel overall. But I'll mention more about the final exam, once I hear from the department, how it will be structured and that sort of thing. So just kind of keep a lookout for any posts that I make about the final exam. All right, so that's just a kind of an overview of all the announcements. It's all on the course website, so make sure you look through the last few posts I made on our news feed there. But really, for today, I'd like everyone to go through and just select which option they are available for. If you're interested for follow-up exam 6, again, it's optional. You don't have to take it. But if you're interested in it, then select which times you are available and which date you would prefer. And hopefully, I'll go through that tonight, and I'll make an announcement when that will be. If everyone has it filled out by 5 p.m. tonight, I'll make an announcement about when that follow-up exam will be later today. All right. So back to integration, and in particular substitution rule. And where we left off last time, we were going through the substitution rule, and I want to kind of go back to our strategy here, because the main kind of tricky thing with substitution rule is how do we choose U? And so, there's no one always work kind of method. You kind of have to try things. Maybe it works, maybe it doesn't. And so our strategy is kind of to base it off of our basic antiderivatives. So we go through and we kind of identify the more complicated piece of our function. And if it's in the form, for example, something raised to the power n, well, then we let u equal what's inside the parentheses. Or if the more complicated piece of our function is a fraction, well, then we might let u equal what's inside the denominator. Or if it's an exponential function, if our more complicated term is an exponential function, well, then maybe we let u equal what's inside the exponent. Or same thing for a trig function. If that's the more complicated piece, well, then maybe we let u equal what's inside that trig function. So we're kind of basing what we choose u off of our basic antiderivatives that we have listed here. Again, this strategy doesn't always work, but for the majority of these substitution rule problems, this is a good place to start. So let's try what we got. Let's go to the example 6 here. So we're going to integrate x squared times sine of x cubed plus 5. And we're going to use substitution rule. So what's the first step for substitution rule? Well, we have to choose what we want for u. And then once we have that, then we calculate du. All right. So we go through and we identify the more complicated piece of our function here. So when I look at this, you can kind of break things down. You can kind of break this function down in a few different ways. But the first thing that I would see is I would break this into an x squared and a sine of x cubed plus 5. And we ask ourselves, which is the more complicated piece of that function? And I would say it's the sine of x cubed plus 5. So what we have here is sine of something. It's a trig function with some complicated x term inside of it. So our first step is to identify u, and I would think as a first attempt, let's let u equal what's inside that sine function. I see parentheses, I let u equal what's inside the parentheses. It's a good place to start. Sometimes you choose a u and it doesn't work, that's okay. And you have to try something different. But let's see if this is going to work. So we choose u. Forget about the integral for a second. And we're just going to calculate the differential du. So derivative of x cubed plus 5 is just 3x squared. Then we multiply that with dx. And then we look at our integral and see how things match up. So when we look at this, and maybe it would be helpful to move any of those extra terms next to the dx. So that x squared, our complicated term there is the sine of x cubed plus 5. So sometimes, at least do this in your mind, take that x squared, it's kind of an extra term that's just hanging out there. Let's move it next to the dx. So I'm going to have this as sine of x cubed plus 5. And then I'll move the x squared next to the dx. And so really where our choice for u, where we can tell that it's going to work or not, is when we compare what we calculated for du with what we have in our integral. So when I look at my integral, these extra terms are the x squared and the dx. Now if I go to my differential, what I calculated for du, I see an x squared dx there. So we have a pretty good match. But not quite. We have this extra constant 3 in front. So that's something we have to deal with, but we can deal with a constant. It's not too much of an issue. So we have this extra constant here in what we calculated for du. So when you have that sort of almost of a match, it tells you you're on the right track for your substitution rule. All right. So how do we deal with that 3? Well, we're going to solve for x squared dx. So we're going to take that 3 and we're going to divide both sides by it. So we'll get 1/3 du on the left, and we'll get x squared dx on the right. And so now we see that we have it perfectly matching. So we're going to be able to substitute this in. So if we go down to our integral, we know down here this is going to become 1/3 du. And then we know the term inside of our sine function here is going to become u. That's what we picked it to be. And so our second step is to go through and just plug all that in. And so we're going to substitute these values into our integral. So we're going to get sine of u times 1/3 du. And from here, this is just now a basic integral that we can do. We know what the antiderivative of sine is. So we'll just move the 1/3 in front, and then the antiderivative of sine is negative cosine. And then we put our plus c at the end. So step 2 was to just plug in all the values for u. Step 3 is to go through the integration. We have our antiderivative now in terms of u. And then step 4 is just to convert back to the original variable. So I'll write this as negative 1/3. So I'll move the negative, put all the constant terms together. And then instead of u inside, we're going to plug in our x cubed plus 5. We'll put that back. And that's step 4. We convert back to our original variable. Now the goal here, once you go through the substitution rule, is you should end up with an integral, and that's what we end up right here. This integral has no x terms in it. Everything has been converted to u. So there's no x terms here. And that's kind of the goal, is once you make that substitution, all of your x terms should be replaced with u terms. So if you still have x's there, you can't go any further. You have to figure out what to do with those x's that are remaining. So everything has to be a u, including the du there at the end. We need that to be a u as well. So if you had dx, we can't leave it as dx. We have to be able to kind of switch over our differential over to du. All right, so let's try another one. So that was sine of, that was one of our trig function ones. Let's try another one. So let's look at the integral of 2 minus x over the square root of 2x squared minus 8x plus 1. And so our first step here is to kind of figure out what we should pick for u. And that's generally the hardest part of doing these. So, you know, if you can get that picked out, the rest of it is kind of a little bit more systematic. All right, so what is the thought process you might go through here? Well, I know for me it usually helps to kind of break this function apart into kind of, when I have a fraction, pull the fraction apart. So I'm going to separate this. I'm going to separate the parts of the function. So if you can just identify u right away, then just identify u and go on with it. But if you're having a tough time trying to pick what u is, kind of break your function apart and look at each of the individual pieces. So what would I do with this? Well, I would write this as 1 over the square root of 2x squared minus 8x plus 1 times 2 minus x, and then the dx at the end. And so I have my individual pieces now. So I identify what the more complicated piece is. So I would say that fraction is the more complicated term. I have the fraction, maybe I have the 2 minus x, but the fraction seems to be the more complicated term. So I notice that this is a fraction. So I might think it's where I let u equal the denominator. So maybe u would be equal to the square root of 2x squared minus 8x plus 1. But there is an exponent around that entire denominator. So we're going to do something else. So normally we let u equal the denominator when there's no exponent around the whole thing. So it's like a hidden exponent of 1 in the denominator. Here we have that square root. That's an exponent of 1/2. So we're going to do something a little bit different. So instead, we're going to rely on our usual strategy by rewriting that term where we convert the root function into a power, so raised to the power 1/2, and then instead of a fraction, we're going to use negative exponents. So instead of having 1 over the square root of 2x squared minus 8x plus 1, I'm going to write this as 2x squared minus 8x plus 1, and I'll convert that to a raised to the power 1/2, and instead of a fraction, I'm going to use a negative exponent. So it'll be 2x squared minus 8x plus 1 raised to the negative 1/2 times 2 minus x dx. And so when I'm looking at this, I have something now of the form raised to the power n. And so that motivates what we're going to pick for u. So I'll write it down here. 2x squared minus 8x plus 1 raised to the negative 1/2 times 2 minus x dx. And so we have that form raised to the power n. So our first kind of attempt at picking u, and hopefully this works out, we're going to let u equal what's inside the parentheses. So we're going to let u equal the 2x squared minus 8x plus 1. And then forget about the integral for a second. Let's just take that u value that we figured, that we kind of picked, and let's calculate the corresponding du that would go with it. So differentiate 2x squared minus 8x plus 1. The derivative of that would be 4x minus 8. And then we take that whole thing and multiply by dx. And when we go to our integral, this is what we're trying to do. We know this thing is going to be u. So our extra terms here are the 2 minus x dx. And so for this substitution to work, we need to be able to kind of produce those extra terms in what we calculated for du. So if we look at what we calculated for du, we have something to work with here. And what we're going to try is we're just going to try factoring this as much as we can until we see something that looks like our extra terms. So we're going to try to factor this. So it's not a clear match right away. 4x minus 8 times dx doesn't look too much like that 2 minus x dx. So it's not a clear match. So see if you can factor it. So when we factor a little bit, I can factor a 4 out. So that gives me du is equal to 4 times x minus 2 dx. That's looking a little bit better. But my extra terms back down to my integral there is 2 minus x. I have an x minus 2. So we can factor out a negative 1, and that would flip the order. So we go a little bit further, and I can factor out a negative 1. So I get 2 minus x then dx. So du is equal to negative 4 times 2 minus x dx. So factoring out a negative 1 kind of reverses the order of the subtraction there. And now if I compare this, everything's looking good. So I compare what I have in my calculated differential for du, and there's a pretty close match here. So that means we're on the right track. The only thing that's a little bit, that might throw a little bit of a wrench into things is this negative 4 that's in front, but that's just an extra constant, so we know what to do with that. So we can just divide both sides and get negative 4 du is equal to 2 minus x dx. So that extra constant term, we can kind of work with that. So when I go to do my actual substitution, we know that the complicated term that's going to become u, but then these extra terms are going to become negative 1/4 du. That's going to become part of my differential. So let's kind of go through and now go to step 2, plug everything in. So let's make all of our substitutions. So we know that the complicated term is going to become u raised to the negative 1/2. And then the 2 minus x dx at the end, that's going to become negative 1/4 times du. And now it's just a function with a constant multiple. So, maybe to make this look a little bit nicer, it looks a little weird having the negative 1/4 there. So maybe we put that in front of the integral just to really remind ourselves that it's a constant multiple. You don't necessarily have to show that step, or maybe you just do it automatically, either way. So we really only need to worry about integrating that u to the negative 1/2. So the negative 1/4 just stays there in front, And then we do power rule for that u term. So if we add 1 to the exponent, we get u raised to the 1/2. We take that new exponent, flip it, put it in front of the u, and that's our integration. That's where we've actually done the antiderivative. So notice when we do the antiderivative, now as soon as I put that plus c at the end, as soon as we find the antiderivative, the integral sign is gone and the du, the differential part, is gone. So both of those drop out as soon as we find our antiderivative. Let's clean it up a little bit. So negative 1/4 times 2 is negative 1/2. And then we have u to the 1/2 plus c. And then our very last step is just to convert back to our original variable. So we have the negative 1/2 in front, and then instead of u, we're going to put in 2x squared minus 8x plus 1. So we end up with negative 1/2, 2x squared minus 8x plus 1, all raised to the positive 1/2 plus c. And there's our antiderivative. Back in terms of x, we're done. So, you know, I'm giving a little bit more work than you would probably show for some of these, but I'm trying to just kind of explain the thought process, especially in step 1 up here. You know, up here I'm probably showing a little bit more than, you know, what I would expect you to do, but you know, I'm trying to explain the thought process when you first approach these. All right. So that one was a little bit more difficult. Let's kind of back off for a second. Do a nice easy one. Integral of e to the kx. So here k is a constant. So when we look at this function, what do we see? Well, we see e raised to something other than just x. So this tells us we have this format of e raised to something. So we're doing the integral of k times x. And because it's not just an x there in the exponent, it tells us we need to use substitution rule. And so our strategy is to, well, let's take what's in the exponent, and that's what we're going to pick for u. So we're going to let u equal kx. Once we pick u, our hand is forced. We have to calculate du then, based on what we picked. So what's the derivative of k times x? Well, that would just be constant k, and then we multiply that result by dx. So that's how we calculate a differential. And so when I look at my integral, we know the k times x up here is going to become my u, and the only thing extra there is the dx. So if I compare that to what I just calculated for my differential, we do have a dx. But we have this extra constant, and that's okay. We know what to do with an extra constant term. We can kind of move it over to the other side, divide both sides of our expression there by k. So we're going to solve this for dx. And we end up with 1 over k times du is equal to dx. And so now we have all the pieces that we need to kind of plug into our function and replace everything and get it all in terms of u. So that's the ultimate goal here, is we want all those x's gone and we want to have them replaced with u terms. So when we do that, we're doing the integral of e to the kx. So let's plug everything in. So the kx is going to become u, so we end up with e to the u. And then we know dx is going to become 1 over k times du. So we put that next. Then we just do the antiderivative. And this is one of our basic forms. So we know what the antiderivative of e to the u is. It's just e to the u. So when we do our antiderivative here, it's just e to the u. And normally it's a good idea to take any constant terms and put them in front. So I'm going to put that 1 over k in front. And then we have plus c. And then the very last step is let's convert this thing back to x. So instead of u up there in the exponent, we'll put our kx back in there. And that's it. So our antiderivative here, once we get back to our original variable, is 1 over k times e to the kx plus c. Now, these are kind of what we maybe call like a k-form or something like that. So these are definitely on the easier side of substitution rule. And, for right now, I'd like you to show your work for these. But, once we move on into Calc 2, you're probably not going to show your work for this. You probably have these almost memorized. So there's a couple different of these k-forms here. Might have, call them like k-form integrals. So it's like a substitution, an easy substitution rule ones. So we might have like e to the kx, and the antiderivative is just 1 over k e to the kx plus c. Maybe something like cosine of kx. So what's the antiderivative of that? Well, the antiderivative of cosine is sine, so we end up with sine of kx, and then we have a 1 over k in front. What about the integral of sine of kx? Well, what's the antiderivative of sine? It's negative cosine. So we get negative cosine of kx, and then we also end up with a 1 over k in front. So altogether, we end up with a negative 1 over k in front. And these are probably our 3 more common of these sort of really easy k-form substitution. So, for right now, I want to see your work while you're kind of developing this practice of going through and showing your work for a substitution rule. I want to see the steps. But, once you get the hang of these, and in Calc 2, these are types of antiderivatives that we really wouldn't expect you to show any work. You probably just kind of have these memorized. You do them enough, you have them memorized. Particularly in Calc 2, we're going to definitely see these ones a bunch. So we'll be doing integral of cosine 2x, integral of sine 2x. We'll be doing those a whole bunch. So, the behind the scenes is really a substitution rule, but you probably have these memorized and be able to kind of do them without showing all the work. But for right now, I want to see it. So eventually, you'll have these memorized. That'll be Calc 2. For right now, even something kind of as simple as this, I do want to see your work here. All right, so just a kind of a mention, for even these basic ones, we want to see your work here. Let's try another one. Integral of tan x. So substitution rule, I feel like we're doing so many examples, and it's really good. I think doing as many problems for substitution rule, it's the best way to prepare for Calc 2. So, we're getting down to the end of the semester, assuming most everyone's going to be taking Calc 2 next semester. And if you really want to prepare over winter break, kind of dust things off, study something over winter break, substitution rule is really it. So we're going to use it so much in Calc 2. where if you can really get a hang of it now, you're going to be you're going to be in really good shape for Calc 2, because we basically use substitution rule in most of the sections that we cover. Not all, but in a lot of them. So if you can really master substitution rule, you are in very good shape moving into Calc 2. All right, so let's try another one. Integral of tan x. So, all right, when we look at this thing, it's not one of our basic integrals. So if we go to our derivative charts and our integral tables, this is not one of our basic integrals. And so the only other technique that we have at our disposal is substitution rule. So we're going to try substitution rule here. And as it stands, there's not very much to go on. So the question is, how do we choose u? Well, all we have there is a tan x, so maybe we try u equals tan x. I mean, that's really all we could pick. That's our only choice here. If we're going to do something with the integral of tan x as it's written, that's all we could do. So, all right, we've picked u. We calculate du, and this is where we can tell if things are going to work out or not. So what's the derivative of tan? It's secant squared. And if I look at my integral here, I do not see a secant squared anywhere in the original integral. So it doesn't mean this can't work. It's just going to mean that it might be much more difficult. So this is a good indication if when you calculate your differential du and you get something that in no way kind of appears in the original integral, nothing even close, well then you need to try something else. So what could we do with tan? We've done it before. Is to kind of rewrite it in terms of sine and cosine. It's the only other option we really have to work with here, is try to use a trig identity. And tangent is sine over cosine. All right. Well, that gives us a little bit more to work with. Again, we're thinking we're going to do substitution rule. And a lot of times with a fraction, it's helpful to kind of, again, break that fraction apart. So let's write that as 1 over cosine x times sine x. And when I look at this, I'm trying to identify what the more complicated term is. And so I would say it's this fraction here. And so we have this format of 1 over something. So if I'm going to do it this way, I might pick u to be cosine x. And so then I want to calculate du. So what's the derivative of cosine x? Well, derivative of cosine x is negative sine x. And then we multiply by dx when we're calculating a differential. And we can really tell if this substitution really has a chance of working by comparing what we get for our differential with what we have in our original integral. So if I look, kind of the leftover term in the original integral is sine x dx. And except for that negative, that's basically what we have in our differential du. So I see that these are almost a perfect match. So that tells us we're on the right track. So we still have to deal with that negative, but again, a constant multiple in front there is not an issue. So when I solve my term here for du, I would end up with -1 times du is equal to sine x dx. So just divide both sides by -1. So now we just put all the pieces together. So 1 over cosine x times sine x dx. And we know the cosine x there, that's going to become u. And we know the sine x dx, that's going to become -1 times du. So that's step 2, is just to plug everything in. So we get 1 over u times -1 times du. All the x's are gone, so that's good. All the x's are gone. So now we can do our integration. So what's the antiderivative of 1 over u? It's natural log absolute value u, and then I'll put that -1 in front. Just a constant multiple, so easier to move it in front. And then we get our plus c. And we're done with the integration now, so the integral sign and the differential now are gone. We don't have to worry about those anymore now that we have our antiderivative. And then step 4 is to convert back to x. So negative natural log of absolute value. And what did we pick for u? It was cosine. So we end up with negative natural log of absolute value cosine x. Now I'm feeling like this is different. If I'm remembering back, if we were going to look this one up on an integral table, we might have this a little bit different. So another if you were to look this up on an integral table, and we'll kind of eventually get to that point with this, you might see the integral of tan x is equal to the natural log of absolute value secant x plus c. So that looks a little bit different. Well, how can that be? How can we have two different antiderivatives? Well, we don't. We can just simplify the one a little bit more. Not necessary to do it, but just to see that we do have an answer consistent with what we might see on an integral table. When we have a negative coefficient here in front of the natural log, we have a log property that lets us take that constant term in front of the log function and bring it inside the log function. And when we bring it in, it becomes an exponent for everything that's inside the log function. So it's going to become an exponent right up there on around our whole cosine term. So another way to write this would be the natural log of absolute value cosine x raised to the -1 power plus c. And cosine x raised to the -1 that's how secant is defined. That's just 1 over cosine. That's secant. So 1 over cosine is how secant is defined. So, that might happen. You do an integral one way, I do an integral some other way, and we get answers that look different, but it turns out that they're the same. All right. So that's, kind of the approach to take on these is if you try something and it doesn't look like it's going to work, well then see if there's something else and maybe try a different U, and maybe that one will work. So it's almost a little bit of trial and error. But once you do the hang of these, you'll kind of know more or less what to pick for you. Now it turns out, if anyone wants a little bit of a challenge, it turns out that you can make this substitution work. So if you want to try that one, it's a nice little challenge. You're going to have to use some trig identities, but see if you can get that substitution to work. It's not how I would do it. If I were trying this problem fresh, I wouldn't do it that way, but you can get it to work. So see if you can. Might be a little bit nice, fun challenge there. All right. Let's try another one. Integral of x cubed times square root 1 plus x squared. And this one's going to be kind of one of our trickier ones. So when we look at this, what do we have? Well, we have a root function. So let's do what we normally do with root functions and write that instead as a power. So that might be something good to do. So I would consider that my more complicated term. So let's put that first, and then I'll move the x cubed next to my dx. Kind of get all the loose terms there next to my dx. All right, so when we look at this, what do we see? Well, we see something of the form, something complicated raised to the power n. So when we go and try to figure out what we're going to pick for u, I see parentheses now that we've rewritten it, so I'm going to let u equal what's inside the parentheses. So 1 plus x squared. Forget about the integral for a second. We go through and calculate du. So what's the derivative of 1 plus x squared? Well, it's 2x dx. And so we know this piece we know what's going to happen with this piece. That's going to become just u raised to the 1/2. So that's not going to be an issue. But if we look at what we have here, kind of if we look at those remaining terms, the x cubed and the dx, that doesn't really match up with what we just calculated for du. Now we have a little bit of kind of room to work there with the x cubed. And so the idea is we calculated du and we got an x dx. So that's really what we're seeing here when we look at this, is we have an x dx. Comparing that to our original integral, we have an x cubed dx. So let's see if we can kind of produce an x dx in the original integral. So what we want is an x dx up here. Well, x cubed, what is x cubed? It's x times x times x. So we could actually split up this x cubed. So if we do that, we could write it, we'll keep the 1 plus x squared raised to the 1/2, and then we'll split up that x cubed. It's really x times x times x, but we'll write it as x squared times x dx. So now if we're comparing, things are looking a little bit better. We have an x dx here. We know this is going to become u. And the only thing that's kind of left there that we have to deal with is that x squared right in the middle. So the goal when we're trying to do these substitution rule problems, we want to replace all the x terms that we have with u terms. All the x's that we see, we want replaced with u's. So the dx has to be replaced. All the x's need to be gone. So the 1 plus x squared, we're good with that. The x dx, we're good with that. It's just that x squared that's in the middle. And so we have kind of two pieces of information to work with. So when we start setting up our substitution, we pick u. So we said u is 1 plus x squared. That's something we can work with. Just like when we calculate du, what did we get? We got 2x dx. And in our integral, we had x dx. Kind of took a little bit of work to get there. We have this extra constant term, so what would we normally do? Well, we would solve for x dx. So we work with that equation to kind of get what we need. So divide both sides by 2 gives me 1/2 du is equal to x dx. So this x dx here at the end, I know that's going to become 1/2 du. So the question is, what about that x squared? Well, just like we can work with that differential equation down at the bottom, we can also work with our equation for u. And so we can work with that equation. And so sometimes we might want to solve for x. In this case, we have an x squared that's left over, so let's solve this equation for x squared. So we kind of have two things to work with here. So you might have to use both of them if the substitution is not a perfect fit. So if we solve that for x squared, we'll subtract 1 from both sides, and that gives us u minus 1 is equal to x squared. And now we know that this is going to become u minus 1. So we have all of the x terms, and we know what they are now in terms of u. So that's the next step. Let's just actually plug everything in. So we're doing the integral of 1 plus x squared raised to the 1/2 times x squared times x dx. And we said u was going to be 1 plus x squared. And we also said that, so this is going to be u. We said the x dx was going to become 1/2 du. And then the x squared there in the middle, that was going to become u minus 1. So let's actually go through and just make all those changes. So we're going to have the integral of u to the 1/2 times u minus 1 times 1/2 du. So that's step 2. Go through and just get everything to in terms of u. So all the x's are gone now. So if you have any x's left over, you got to keep working until you get rid of them. So you might have to kind of look at these two pieces of what you've chosen and what you've calculated, u and du, and see if you can kind of solve one of those equations to get rid of the remaining term, any of the remaining terms. So we were able to do that. So now we have an integral that's all in terms of u. So we want to do the integral of u to the 1/2 times u minus 1 times 1/2. We got to do a little bit of algebra first before we get this ready to integrate. So we're going to distribute the u to the 1/2, do the multiplication. And that 1/2 is a constant multiple, so let's get that out in front of the integral. So I'll move the 1/2 in front, and then when I distribute, I get u to the 3/2, so I add the exponents, and then minus u to the 1/2. And then let's not forget our differential there at the end. And now that's an elementary form. That's a basic integral, so we can just do power rule a couple times. So now we're ready to do the integration. So the 1/2 is a constant multiple. It stays in front. And let's do the antiderivative of that first power function. So the variable is u. If we add 1 to the exponent, bumps it up to 5/2. Take that new exponent, flip it, put it in front, so 2 over 5. Then we're subtracting, and we go to the next power function. Again, the variable is u. Add 1 to the exponent, takes us up to 3/2. Take that new exponent, flip it, put it in front, so 2/3. And then we put our plus c there at the end. Almost there. So we're done with our antiderivative. We've done the antiderivative. So the integral sign and the du now are gone. So as soon as we find the antiderivative, both of those drop out. What's left then is to just go and convert back to x. So that's step 4. And as we do this, you might want to try to simplify any constant terms. So I might distribute that 1/2 that's in front. So I would end up with 1/5, and instead of u, I'm going to be putting in whatever we said u was. So in this case, the 1 plus x squared. So I'll have 1 plus x squared raised to the 5/2. And then if I distribute the 1/2 that was in front, again, just multiply it with the constant multiples there. 1/2 times 2/3 gives us 1/3. So the 2's just cancel. And then instead of u, put it in as 1 plus x squared. So our antiderivative here is 1/5 times 1 plus x squared raised to the power 5/2 minus 1/3 times 1 plus x squared raised to the power 3/2. And then let's not forget plus c there at the end. And there's our antiderivative. All right, so a lot of practice here. So really, the more you practice substitution rule, the better off you're going to be. So it just comes with practice. So I think seeing a lot of these examples, try some, come back, rewatch parts of the lecture. The more you can do of these problems, the more prepared you're going to be moving into Calc 2. All right. So we're going to do a couple more, but we're going to do them in the context of doing definite integrals. And so we ended last time, we looked at method 1 for definite integrals, and this is where we did our substitution rule just like we normally would, and we did not change the limits of integration. And then we converted our antiderivative back to the original variable just like we normally did, and then we would just evaluate like normal for a definite integral. We're going to try the second method, which is we basically do the same steps. The only difference here is we're going to change the limits of integration from x to u, and kind of the benefit of doing this is then when we go to once we have our antiderivative, we do not have to convert that antiderivative back to x. So let's try an example. So we did example 1 using method 1, where we kind of didn't change the limits of integration at all. We're going to do example 2, where we actually changed the limits of integration. But the actual substitution rule part of it, choosing u, calculating du, that's going to be the same. All right, so let's try this one with method 2. So it helps to rewrite, we're doing the integral from 1 to 2 of this function 1 over 3 minus 5x all squared. A lot of times to make the notation a little bit nicer, the dx goes in top if the numerator for a fraction is just 1. But really we could think of this as the integral from 1 to 2 of 1 over 3 minus 5x squared. So that's just an equivalent way of writing it. So you might see it both ways. And it's going to be, we have a fraction there, but there's an exponent around that entire denominator. So we're going to go with our usual strategy then of rewriting it with a negative exponent. So instead of 1 over something raised to the power 2, we'll write this as 3 minus 5x raised to the negative 2. So we're just going to use a negative exponent. And then we have our dx at the end. All right, so it's a complicated integral. We see parentheses. Step 1, we want to pick u. So we're going to let u equal what's inside the parentheses. So 3 minus 5x. Then we calculate du. So the derivative of 3 minus 5x is negative 5. And then we multiply by dx. So if I compare what I have, the 3 minus 5x, that's going to become u. And I only have a dx there at the end. There's no other terms. So we do have a dx there in what we calculated. That negative 5 is sort of an extra constant. We know what to do with that, though. So we're just going to divide both sides by negative 5. We're going to solve for dx. So that'll give us negative 1 over 5 du is equal to dx. So we know what's going to happen with our differential there at the end. And let's see the kind of the piece that's going to be different now. So we know our integral, let's start kind of putting the pieces in there. So we know that the 3 minus 5x, that's going to become u. So we'll end up with u raised to the negative 2. The dx there at the end, that's going to become negative 1 over 5 times du. And so all of that's standard substitution rule. Nothing different here. What's going to be different is how we deal with those limits of integration. So what we're going to do is we're going to convert those limits. So our upper limit was x equals 2, and our lower limit was x equals 1. And what we're going to do is we're just going to take those x values and plug them into our equation for u. So our equation for u was 3 minus 5x. So when I plug 2 into that, I get 3 minus 10, which is negative 7. And when I plug x equals 1 into that, I get u equals negative 2. So I get 3 minus 5, which is negative 2. And so that's what I'm going to do. I'm going to change those limits of integration I'm going to replace them with those new ones I just calculated. And to just really remind myself that I'm making this change, I'm going to write those limits of integration as u equals -7 and u equals -2. All right, so now that's it. That's all that's new here. So now we go through, find the antiderivative just like we normally would. So, well, what's the antiderivative? -1/5 is a constant multiple, so we'll put that in front. Our power function is u raised to the -2, so we're just going to use power rule. So we'll add 1 to the exponent, bumps us up to -1. And then we take that exponent, flip it, put it in front, so we get 1 over -1. And since we're doing a definite integral, we don't need to worry about plus c, but we are going to put our evaluate line. So we're going to evaluate from -2 to -7. Before we do the evaluation, let's simplify our antiderivative. So we get just positive 1/5 in front. And then instead of having u to the -1, a lot of times it's a little bit more helpful to rewrite that back as a fraction. So that would be 1 over u. And then the last step is to just evaluate. So we have our antiderivative, we simplified it down. We don't need to convert that antiderivative back to x because we changed the limits of integration. So now we just evaluate that like usual. So the top number goes in first. We get -1/35. Then we subtract and we plug in the bottom number, which was -2. So we get -1/10. And if we wanted to, we could simplify that expression down a little bit more, but perfectly fine. That's our answer. To just leave it like that. All right, so that's doing definite integrals involving substitution rule. So I think well, we'll do one more, and that'll finish it off. So I'm going to run a little bit late today. Really, we're just doing a bunch of examples here. So by now, we've done enough where you can definitely complete all the homework problems for these two sections. But it's good to just see, examples and to just go through as many as you can. So we'll try one more. But like I said, we've done enough now where you should be able to get through all the homework problems. So let's do the integral from 0 to 4 of x over the square root of 2x plus 1. And let's start with doing the substitution rule. So, why do we think we're going to have to use substitution rule here? Well, I see that square root, and I see something that's a little bit more complicated underneath that square root. So that's an indication that we might have to use substitution rule. And to help us out, we've mentioned this before, but instead of leaving the root sign, let's write that as an exponent, and instead of having a fraction, let's use a negative exponent. So we'll write this as x times 2x plus 1 raised to the -1/2 dx. So instead of having that square root 2x plus 1 in the denominator, we're going to change that to 2x plus 1 raised to the -1/2. All right, so we see that we have u, or we see that we have something a little bit more complicated inside parentheses. So that's our choice for u. We're going to let u equal what's inside the parentheses. So that's 2x plus 1. All right. Well, as soon as we pick u, then we should calculate du. So derivative of 2x plus 1 is just 2. Multiply that by dx. And we just want to compare now. So we have a dx here. Again, the constant multiple that's in front 2, that really doesn't that really doesn't help us at all. It doesn't really hurt us at all. We can deal with that too. It's the variable terms that can make or break us. So we have a dx. We go up to our original integral. We have a dx here, so we definitely have that. We know the 2x plus 1, that's going to be u, kind of by design. Now where things are a little complicated is we have this x term that isn't immediately clear what's going to happen with that. So we know the 2x plus 1, that's going to become u, and then we know our dx that's going to become part of our differential du, but what about that x? And so this is one of those problems where we have this extra variable term. And when that happens, it can mean a few different things. Maybe we picked a bad u. It happens. But maybe we can work with our little pieces of information here, and maybe we can figure out what that variable term is. And that's what we're going to do for this one. We're going to solve for x. Not too bad to do. We're going to take that equation u equal to 2x plus 1, and we're going to solve that for x. So when we do that, subtract 1 from both sides, divide by 2, and that gives us x. And so we're going to be able to use this u minus 1 over 2 in place of that single x term. What about our differential? Well, we go through our usual routine for that. This one's nothing too different here. We're just going to solve for the dx. And so we get 1 over 2 times du is equal to dx. So let's put all that in. And we have some choice here. Do we want to go through and use method 1, where we get our antiderivative back in terms of x, or do we want to switch over the limits of integration? Just for something different, let's do method 2 here, where we'll actually change over our limits of integration. So you can do either way. You can either leave the limits of integration as is, or you can convert them. We're going to do this one where we convert them. It's up to you how you want to do it. Same amount of work, just a different order. So whichever one you like better. So let's do our limits of integration. So so our limits of integration are x equals 4, that's our top limit, and our lower limit was x equals 0. And to figure out our new limits of integration, we're going to plug these into our equation for u. So u equal to 2x plus 1. So let's see what we get. So when I plug 4 into 2x plus 1, I get 8 plus 1, which is 9. So my new upper limit is going to be 9. And then what about for my new lower limit? Well, I'm going to plug 0 in, so I get 2 times 0 plus 1. It's just going to be 1. So my new limits of integration are going to become 1 and 9. All right, so let's rewrite our integral now with everything changed over. So we know our limits of integration are going to be u equals 1 and u equals 9. Again, I like writing u equals there just to remind myself that I did actually change the limits of integration. That x term we know is going to become u minus 1 over 2. The 2x plus 1, that's going to become u to the negative 1/2. And then the dx there at the end is going to become 1/2 times du. So there's our integral now, and everything's been switched over to u, so we're good to go. Now we can go about simplifying if we need to, and then getting the antiderivative. So first, we have a couple constant multiples here. So we have a couple 1/2s floating around. Let's multiply those together and move them in front. So we'll get a 1/4 in front. And then we have u minus 1, u to the negative 1/2 du. And we have a product there. So far, our only way of handling a product is to try and do the multiplication. So we're going to distribute, take this u to the minus 1/2 and just distribute it to our terms there. So we get u to the positive 1/2 minus u to the negative 1/2 du. And now it's just two power functions, so we can do this. So the 1/4 stays in front. Our first piece there is the u to the 1/2, so let's add 1 to the exponent, bumps us up to 3/2. Take that new exponent, flip it, put it in front, so we have a 2/3. Then we're subtracting. Our next power function, it has variable u. We add 1 to the exponent, takes us up to 1/2. Take that new exponent, flip it, put it in front, so 2/1. And we're doing a definite integral here, so we don't need to worry about the plus c. We'll put our evaluate line, which is u equals 1 to u equals 9. Simplify the antiderivative if needed. So we can do a little bit of simplifying here. So just distribute that 1/4 that's in front. So we end up with 1/6 u to the 3/2 minus 1/2 u to the 1/2. And we're evaluating from u equals 1 to u equals 9. And then the very last step, plug in. So we just evaluate. And we can evaluate this because our variable and our limits of integration are the same. So top number goes in first. We get 9 to the 3/2 times that 1/6. Then minus 1/2 times 9 to the 1/2. And then when we plug in 1, we're going to subtract and plug in 1. So we get 1/6 minus 1/2. And any power of 1 is just 1. So 1 to the 3/2 power is just 1. 1 to the 1/2 power is just 1. So there's the value of our definite integral. I mean, we could go through and simplify that. There's a little bit of work we could do. 9 to the square root of 9 is 3. So we could do some arithmetic there. But we're just worried about getting this definite integral. So as soon as we get a numerical answer, that's fine. We can just stop there. So you have some options for definite integrals with substitution. You can either convert the limits of integration like we did here, or if we go back to the first example we did, you can leave the limits of integration alone, and then once you have your antiderivative, you would convert back to the original variable. So whatever happens once you're ready to evaluate your limits of integration and the variable pieces of your antiderivative, they should be the same. So everything here, our limits of integration for this example we did last time, we got our antiderivative back to x, and our limits of integration were in terms of x. So it has to be the same variable before you start plugging in. So once we got those to be the same variable, then we were able to plug in. Same thing for example 2, but this is where we converted the limits of integration. But again, we got it to a point where everything was the same variable. So our antiderivative was in terms of u, and then our limits of integration were in terms of u. Once everything's the same variable, then you can plug in. And then finally, same thing for the one we just did. So we got it to a point where our antiderivative and our limits of integration were all the same variable. So that's why I like writing the limits of integration as u equals or x equals, just to remind myself, did I convert them or didn't I convert them? So it's easy to kind of lose track when you're doing these. All right. So I apologies for the late start and going over. You know, like I said, it's just helpful to have a lot of examples. So, you know, really we've done a bit of overkill in examples for this section, but I think it's really helpful for you once you're going through the homework. You can kind of just refer back to some of these and try them for yourself. So having plenty of examples is and trying them for yourself, I think, is the way to go. So so we'll stop there. Have a nice fall break. Make sure you read through all the announcements that I posted on our course website. Fill out the survey for when we're going to schedule follow-up exam 6. Have a nice fall break. No office hours or recitations on Thursday, Wednesday, Thursday, Friday. But if you do have questions, I'll be checking our website. So if you want to post a question on our website, I'll be checking over the break. So you can always ask me through there. So all right, have a nice Thanksgiving, nice break. Get a little bit of relaxing in, and we'll see everyone next week. Bye-bye.